So welcome back everyone. So in POEMA we have great ESR and some of them will give some talk during this third workshop. So now we are glad to hear Soodeh Habibi, who will speak about an interior point method for solving low-rank semi-definite programs. Thank you, Soodeh. We will listen to you.
Hello everyone and good morning, and thank you very much for the introduction. Today I'm going to talk about an interior point method for low rank semi-definite programming, and here it is. In this first slide, I will give a brief introduction to the methodology used within the research. And in our research, we are solving large and sparse low-rank semi-definite programs, SDP, by using an interior point method. The general bottleneck of interior point method is assembling and solving the short complement equation, in which matrix becomes increasingly ill-conditioned as the interior point method makes progress toward the solution. Instead of the direct solver, which is Cholesky factorization, we are using preconditioned conjugate gradient, or PCG here. And also, we are proposing some new preconditioners for the low-rank situation. And also, the efficient preconditioners allows PCG to converge to an approximate solution of the linear equation in a few iterations, independent of the ill-conditioning of the short complement matrix. So here is the general overview of the topics that I will discuss today. We start with an introduction, which outlines some assumptions. After that, we look at solving the short complements equation, and also we go through the ill-conditioning of the scaling matrix. And then we introduce some preconditioners. We talk about some preconditioners, H tilde and H alpha, which H alpha preconditioners is the one that we are working on. And then we talk about some application in TrussTopology optimization. And at the end, we will see some numerical results that shows that how our implementation is working better than most software, or some softwares for SDP. So here, the size n semi-definite program with m constraints are these, and here is our problem, and here is our primal SDP. Because some people might call this one as a dual SDP, but it's our primal SDP. And each matrix in here are real symmetric, and we will also assume that X star is of very low rank. So here we have SDP Lagrangian dual, and which is this problem, and we call it SDD. In this slide, I wrote our assumptions. And first, large and sparse low-rank SDPs are considered for which the number of non-zeros in their data matrices A1 to AM is small. And we assume Slater conditions, and we assume a strict complementarity. Also, we have a sparsity here, and first we define the matrix A to be a matrix which its columns are the vectorized version of the vectorized form of our data matrices A1 to AN. And we assume that a matrix vector product with A transpose, and A transpose A inverse may each be applied in OM flows and memory. Now I want to talk about the interior point method. In each iteration of the interior point method, we have to solve this system of linear equation in variable y. So here's the system, and AIs are our data matrices, and W is the scaling matrix that we will discuss later. So vectorizing the matrix variables allows the last system, which it was this system, this system to be compactly written as this new system, which we call it our Shor complement equation. And now here is our system, and with its special properties that we want to solve. And here D is the Kronecker product of W with W. And as we said before, W is our scaling matrix. So now I want to talk about solving the Shor complement equation. And one of the ways to solve this equation is using CG method, conjugate gradient method, which is an iterative method. But H is very large and sparse, and H becomes increasingly ill-conditioned as the outer interior points method makes progress toward the solution. And also assembling H is very expensive. And so, the successful CG-based solution of this equation rely on an effective preconditioner. So instead of using a conjugate gradient, we will use a preconditioned conjugate gradient. In preconditioned conjugate gradient, we don't need anymore to assemble H, which we said is very expensive. We only have to compute a matrix vector product HZ using the equation, the first equation, which this HZ is this equality, as we can see here. So now I want to talk about the scaling matrix W. W is our scaling matrix, and it captures the curvature of the log depth penalty function. There are three different ways to construct this W. First of them is primal scaling, and if we consider the set of x hat, y hat, and s hat to be our current iteration, in primal scaling, the W will be equal to x hat. In dual scaling, W will be equal to s hat inverse. And in Nesterov scaling, which is Nesterov scaling is the scaling that we are using, and in here, W will be the unique positive definite matrix satisfying in this equality, which is x hat equal to W s hat W. But in all these three cases, W becomes a progressively ill-conditioned as the interior point method makes progress toward the solution. And actually, this is the mechanism that caused the ill-conditioning. So here, now I want to talk about the preconditioning of the Shor complement matrix. So we said that we need a preconditioner. There is a critical observation that if the solution X star is low rank, W will be low rank as well. So now we use this low rank property, and we will rewrite W, we decompose W into a well-conditioned component and also a low rank perturbation. And this W will be equal to W0 plus UU transpose. And these elements are, and actually W is this, it's written as this. And here, if we consider K to be the rank of the solution, lambda S, which is written here, it will be the smallest n minus K eigenvalues of W, and lambda L will be the co-largest eigenvalues of W, and Vs and Vl will be the eigenvectors for those eigenvalues respectively. And the tau that we have here is something between the minimum eigenvalues of lambda S and the maximum eigenvalues of lambda S. So we said that we decompose W to two parts. Now, by replacing this W in H, which we said H, it was equal to A transpose dA, and D was the Kronecker product of W with W. So we replace this W here, and we will rewrite H as we can see here, and each H will be equal to A transpose W0 Kronecker product WA plus VV transpose. And now this W0 here will be approximated by 2 times identity, and it will yield to H tilde preconditioner, which the first preconditioner that we have here. So if I want to talk about the H tilde preconditioner, I should say that this is Zhang from Zhang and Lavoi in their paper under the title of Modified Interior Point Method for low rank, large and sparse low rank semi-definite programs, and by using a Sherman-Morrison-Woodbury formula, H tilde inverse will be written as this that we can see here. Now I want to talk about the new preconditioner, which is the new preconditioner that our preconditioner actually. But we have the inspiration from the preconditioner from Zhang and Lavoi. And we say that the preconditioner from Zhang and Lavoi was H tilde, which was written as this. And by replacing A transpose A in this preconditioner by identity matrix, we introduced the new preconditioner. And the new preconditioner is H alpha. And H alpha is equal to tau square times identity plus VV transpose. This new preconditioner H alpha has several advantages compared to H tilde. And it is first cheaper to compute, and also it's cheaper to apply than H tilde. And also it requires less memory, and it is perhaps surprisingly more efficient. And I need to add that it also works almost for almost low rank problems, not just low rank problems. Here, for showing that watch of H alpha is nearly a perfect preconditioner, I brought two figures. Here in the figure in the left hand side, we have the distribution of eigenvalues of short complement matrix, which is H, and we can see that there is one distinct eigenvalues, and the remaining eigenvalues are spread from something between 50 to 10 to the 8. And but the second eigenvalue, second figure on the right hand side, shows the distribution of eigenvalues of H alpha inverse H, the preconditioned matrix. And we can see that most of these eigenvalues here are equal to 1, and the rest of them doesn't exceed 1.36, as we can see here. And the preconditioned matrix is actually has clustered eigenvalues with very small condition number, and showing that why H alpha is nearly a perfect preconditioner. In this part, I want to talk about the applications and in TrussTopology optimization, and actually for testing, we are using a TrussTopology problem, which is formulated as a large scale STP with the low rank solution. So I want to talk more a bit about the TrussTopology problems. And TrussTopology optimization is a problem from engineering, mechanical engineering, and civil engineering. And we can assume that we want to, design a bridge like the one that we have in the right-hand side. So we have some nodes and bars and some loads. Then at first we have the initial ground structure like the one that we have in the left-hand side, and this is the initial ground structure of the potential bars. And actually the goal is to find the thickness of bars in this potential ground structure. And in here, these two dark triangles in the corners are our boundary conditions, and TrussTopology optimization actually finds an optimal, which is the optimum lightest structure with stiffest structure, which in this case looks like this, that we can see here. But I need to add that these two figures don't fit together completely, because on the right-hand side in a result, there are so many more potential nodes and than the initial structure in the left-hand side. And that's because in the initial structure, much fewer nodes are connected by possible potential bars and wires, and all of the nodes are connected together. So if we did that for all the nodes from the right-hand side, the picture would be black because all the nodes would be connected together and we wouldn't see anything. That's why that these two pictures, they don't fit together, and it just shows the idea that everything is connected together, and we are just trying to select those ones which are important for us and for the structure. And on the right hand side, there are the results of a much finer mesh. So here it is. And so in this slide, we have this one is one of the formulation of TrussTopology problem. And our STP actually look like this. And in here, X is our variable, and M is the number of the potential bars. And our potential bars are all the connections of all of our nodes, which we have n nodes here. And the matrix inequality in here is large by far, but not that large as the dimension of X. So M is much larger than N. And here, Xi's are very sparse, but the LMIs as such, which is this, is generating a dense matrix for the truss topologies. And here, as we said before, M is much larger than N. And here also it is interesting from the point of view of the method that if Xi lower bound is greater than 0, then the dual solution has a rank 1. And so the problem would be with exact rank 1. But if it is not, and if the Xi lower bound is equal to 0, then the dual solution has almost rank 1. One big distinct eigenvalue, several smaller ones, and the rest will be 0. So that was an overview and a view about TrussTopology optimization. Now I want to move to the numerical result parts. And in this slide, I brought some part of our outputs of solving a truss problem. At the beginning, we are just using a diagonal preconditioner, and it's just multiplied by the inverse of the diagonal of the matrix because it's fast and efficient in the first steps. And as soon as it's not efficient anymore, we switch to the preconditioner, to our preconditioner, to H alpha preconditioner. And here in the last 4 shown iteration, we can see the effort of the H alpha preconditioner, and we can see that till the very end. And even if the matrix is highly ill-conditioned in the step 37, and we have the small error, and but still our preconditioner is working very efficient, and we just need 6 iterations in CG method to solve. So, and here in this slide, I brought a table that shows the result of solving some TrussE problems. I will say what's TrussE problems. And we can see the results here. And by solving these problems by using Mosaic software and also our code, which is called MyIP. And we tested that on through 3E to through 25E problems, and all these problems are actually the same, are different instances of the same problem, but larger and larger. And I need to add that TrussE problems actually are problems with exact rank 1. So they are real low rank problems. And here in this table, we have some columns, and we have the number of variables, we have the matrix size, we have the number of interior point iterations and CPU time for both Mosaic and MyIP, which is our code. And at the end, we have the column that shows the speed up of MyIP with respect to Mosaic. And here, we can see that we could solve the problems with around 200,000 variables and the matrix size of 1,000. But Mosaic couldn't solve problems larger than 217E, and it's because of the memory required by the direct solver. So, and by looking at the speed up column, we can see that how much we are working well. Here in this slide, I brought some figures that shows the result of the last table to understand the effectiveness of our preconditioner better. So in the left-hand side, there is a figure of Mosaic versus R code, MyIP CPU time, and R code has much smaller computational complexity, as you can see here. And in these equations, in this Y, the exponent in this Y, the blue one, which is for Mosaic, is almost 2.5, and the exponent in the red one, which is R1, is 1.5. So we can see that we are 1 magnitude faster than the other one, Mosaic. And they also have almost have a cubic complexity, but we have something between linear and quadratic complexity. And it is showing that how quickly it goes to CPU time with the dimension of the problem. And also it shows that we can predict that we can solve even much bigger problems still by red, which is R1s, before we get to the level of that 10,000 here. Also, the figure on the right-hand side shows the speed up of my IP with respect to Mosaic versus the number of variables. And we can see the speed up and how the speed up is getting higher. It's getting faster, actually. So here again, I have a table that this table is for Truss problems, and we have the result on through 3 to through 25 problems. And these Truss problems are actually the problems that they're almost low rank. For which the preconditioners weren't primarily designed for. They were designed for the low rank problems, but we can see that it also works for almost low rank problems. And we can see that it is still very effective. And again, by looking at the results, we can see that Mosaic couldn't solve problems larger than 217. But we could solve the problems, with the number of variables around 200,000. And again, we can see the speed up column, and we can see how fast we are. And in this slide, again, we have the same figures for these results, and we can see that how our preconditioner is working better and faster on these type of problems as well. Before I talk about the H alpha preconditioner, I mentioned H tilde preconditioner, which was proposed by Jangal Lavoie, and actually that was our work inspiration. So here I brought a table to show that our preconditioner, why our preconditioner is is better than Jangal Lavoie's one. And here is a table, and we tried both preconditioners H tilde and H alpha, which is ours, on the problems through 3 to through 11. And we have the number of IP iterations here, CPU time for both, and also the speed up of H alpha, our preconditioner, with respect to H tilde. And by looking at this column, the speed up column, we can see that, how much our preconditioner is working better. We can just look at the numbers. So our preconditioner is faster. And here in the last slide of the numerical results, I brought again the same figures for H tilde versus H alpha CPU time, and also the speed up of H alpha with respect to H tilde versus the number of variables. and we can see how much the precondition is working group. As we saw for trust topology problems, for low rank and almost low rank problems, we can do quite well. But since the preconditions are much dependent on the data, we are looking forward to have some SDP instances from your side, to be able to try our preconditioner to make sure that it's working good. So that's it, and thank you very much for your attention.
Thank you, Soodeh. So are there some questions? You can write them in the chat or just start to chat if you have some.
So Mohab, may I ask a question?
Of course, you are more than welcome.
Hello, Soodeh. Thank you for the nice talk.
Thank you.
Could I perhaps just see the slide again with the H alpha preconditioner?
Yes. Yeah, here. Sorry.
Okay, so I was just wondering, in the special case of linear programming as opposed to semi-different programming, does it reduce to a known preconditioner?
Sorry, does it? I missed the part.
Yeah. Okay. So if you would work this out for linear programming, so in the special case where the matrices are diagonal, does it then become a known preconditioner?
Yeah, it works better on those kind of linear programming as well.
Yeah, no, but I just mean, does it become a preconditioner that is known from the literature in the special case?
Yes, I think yes, because the problem that we are working on, it includes some linear equations as well. So yes,
Okay.
yes, it is now. It's fine.
If I can add, if we have additional linear inequalities, we still treat it as an SDP. So then the part of the matrix coming from linear inequalities is just a diagonal matrix. So then actually preconditioned by the inverse of the very matrix. So the preconditioner is like the exact preconditioner in that case.
Okay, I see. And I was just also wondering, you mentioned as motivation about two things, the size of the Schur complement matrix, but also the ill conditioning near optimality. But so what is really your prime motivation? Is it more the size or the conditioning?
The conditioning is the.
But I mean, this is a bit surprising because traditionally interior point methods don't suffer so much from ill conditioning of the Schur complement matrix, because close to optimality, you tend to have superlinear convergence. So you do not typically have to construct the Schur complement matrix close to optimality. So you do not really encounter these very ill-conditioned Schur complement matrices in practice.
Yeah, but yes.
No, sorry. So your experience is that you do encounter them with these trust problems.
Yes, exactly. We will have the ill conditioning, and it becomes from the ill conditioning. This ill conditioning actually comes from the calculation, the constructing the scaling matrix, which was W that I talked about. So we have some ill conditioning, and yes, we're trying to solve that.
So just to understand, so you use the Nesterov-Todd scaling matrix, right?
Yes.
And just for my own understanding, did you build on some platform? Did you adapt some existing code, or did you write everything from scratch?
Yeah, from code, exactly.
Everything from scratch in MATLAB.
I'm sorry, Michael, I couldn't quite understand.
Everything from scratch in MATLAB.
Okay, everything from scratch. Oh, that's impressive.
Yeah.
Okay, so thank you very much. That's very interesting.
Just again about the conditioning. So if we want to use PCG, and we need to use it because of the memory. We cannot use direct solver. And if we did not use any preconditioner, then already in the third, fourth iteration of the interior point, there would be no chance to solve it by conjugate gradient at all. It would not converge at all.
Yes. Maybe if I may continue more, I just have one more issue. So what other people have done with such low rank matrix STPs in the past was to use a dual interior point method as opposed to primal dual. And then the advantage is then you exploit the low rank structure in forming the Koleski, the Schur complement matrix, and then still solve the system with preconditioned conjugate gradient. So you know, so I was wondering if it's a good idea also to compare with these dual SDP methods. This is one by Benson and Ye, for example.
It's a good idea, definitely, for these problems, but the thing is that Soodeh only presented one of the problems we solved, so with rank 1. But if we add more constraints, like vibration constraints, which is forbidden, then actually we do not know exactly what is the low rank, or what is the rank of the matrix. It can be 2, it can be 5, so yeah, we have to keep this in mind as well.
Right. Good. Thank you very much.
Thank you, Etienne. Are there other questions?
I have ask.
Yes, Bernard, you can.
So for the SDP problems which are coming from say general polynomial optimization program, the matrices have a structure like so they are moment matrices with a structure which is like Hankel matrix. So can you find adapted? So what would be a good preconditioner for this type of matrices? Or do you have some good preconditioner here?
Sorry, can you repeat that? What type of matrices you mean?
So a moment matrix which is not sparse.
Yeah.
And it has a structure which is like a Hankel matrix. So you have some repetition of coefficients.
I haven't done any experience, and then maybe Mikkel has some experience that we can share.
Actually, that would be just the next line of research, because the structure of the data matrices can be used in the code as well, but it's independent of the preconditioner. So it is just another way how to even more improve the efficiency of the code.
Yes, but I think the structure will also have some consequences on the conditioning of these matrices. So these Hankel matrices, they are not so nice from this point of view, generally.
Well, we don't know at the moment.
Okay.
Thank you, Bernard. Any other question? We have some time.
Perhaps there was a question in the chat about the size of the matrices. If Soodeh
yes.
show if Soodeh could show one of the tables, there we can see the sizes.
Yeah. So here, the table for Trust E problems, and we can see the size. Here is the size of the tables, the number of variables, and here is the matrix size.
The lim is the size of the linear constraints because we still have linear constraints.
Okay. We have no more slides.
Mohab, may I just ask one more question?
Yes, you can.
So there you had a slide about the rank of the dual optimal solution for the TrussTopology SDP.
Dual optimal solution of the trust. Oh, here you mean? No.
Yes, that's that one.
Yeah.
Yeah. So I didn't understand the third bullet point. So which I do you refer to?
The I is the the number of the potential bars. I from 1 to m.
So you mean for all I?
Yes.
So if all the xi bar are positive, this is what you mean?
Yeah, it means that if we have the the zero lower bound. So.
Oh, okay. Sorry, these are the bounds. Okay, sorry, my mistake.
Yes.
Okay, thank you.
Yeah.
Okay, thank you.